So about 2 weeks ago, the AlphaGo team by Google DeepMind, they published their latest paper in the AlphaGo series. This time it's called AlphaGo Zero. And I want to dive into some of the technical details that make this version of AlphaGo so much better than the previous version that beat Lee Sedol. Are you ready to dive in deep? My name is Xander, and welcome to Archive Insights. So I want to go over 5 of the main changes that were implemented in the latest AlphaGo paper. So the first thing is that in comparison with the previous version, AlphaGo Zero trains entirely from self-play. That means that it does not use any data sets from human professional Go players. It learns the game of Go entirely from scratch using only self-play. The second thing is that the previous version used a lot of predefined features that were handcrafted for the game of Go. The new network, AlphaGo Zero, uses none of those features and learns entirely by observing the board state. Another interesting thing for me was that they changed from a normal convolutional architecture based on inception to a completely residual architecture. I guess ResNet is here to stay. Another major tweak to the network is that instead of having a separate policy and a value representation network, the two are now combined into a single large network that does both of these things. And then finally, they replaced the Monte Carlo rollouts with a simpler tree search approach that uses this single network to both do value prediction and to come up with very strong moves. So let's go over all of those tweaks one by one. So we start out with a board position in the game of Go. The game of Go consists of a 19 by 19 grid. So you have 19 by 19 squares, every single one of them containing either a white stone, a black stone, or nothing at all. What they decided to do is they create a separate feature map for the white stones and for the black stones. So that means that for all of the white pieces on the board, you have a 19 by 19 binary matrix which just says a 1 whenever there is a white piece on that position and a 0 when there is not a white piece there. In the black feature map, you do the same thing, a 1 whenever there's a black stone and a 0 when there's nothing at all. Now, instead of simply having those two planes that actually represent the current position of the board, they also include 7 other feature planes which represent the 7 past board states. So they include a little bit of a history of the game inside these board representations. I was kind of surprised as to why they did this, so I asked the question on their Q&A on Reddit, and the reply I had is that this history actually acts as some kind of an attention mechanism. So if you also include the past moves of your opponent, then your network can actually focus on what the opponent was playing, and this works as some kind of an attention mechanism. So kind of interesting. Additionally, there are also some Go-specific rules that require you to take into account the recent history in order to play moves that are allowed by the game. So we end up with this 19 by 19 by 16 board representation. 8 feature maps for the white stones and 8 feature maps for the black stones, all of which are binary numbers, either 1 or 0. And then in order to play the game, you need one final thing. You need to know whose move it is. Is it white's move or is it black's move? And so for this, in theory, you only need a single bit. But the Google DeepMind team, they actually decided to duplicate this bit and to actually duplicate it over the entire 19 by 19 grid. The reason for this is mainly an implementation detail, because if you want to feed this whole representation, 19 by 19 by 17, to a convolutional network, it's easier if you can just duplicate that last bit over the entire feature frame. So we take this input board representation and then we're going to feed it to the network. So the previous version of AlphaGo actually used a standard convolutional architecture, whereas this new version of AlphaGo Zero, they replaced the standard convolutions with a residual network. So that means that in every single layer, there is actually a pathway from the input directly to the output without any convolutions being applied to it. And the major reason why residual connections turn out to work so well is because they allow the gradient signal that is used for training this network to actually pass straight through the layers. So if you are early on in your network training process and your convolutional network is not really doing anything useful yet, you can still allow your useful learning signals to pass through those layers in order to fine-tune other layers. So we take our board representation, run it through the residual network, and then we end up with this feature vector. And now from this feature vector, we need to create 2 things. The first thing they create is the value representation. This is simply a number between 0 and 1 that represents how certain the AlphaGo network is that it is going to win the current game. The second part of the network output is the policy vector, and this is actually a probability distribution over all the possible moves that AlphaGo can play given the current position. And now obviously we want to train our system to play very good moves, so the whole board representation actually needs to lead to high probabilities of good moves and low probabilities of very bad moves. That is the whole goal of training the system. Okay, so now that we've looked at the network architecture, going from a board representation through the residual connections onto a value representation and a policy vector, how do we train this thing? If we look at the version of AlphaGo that beat Lee Sedol, this version was actually trained in 2 stages. The first stage used supervised learning on a dataset of professional Go moves, whereas the second stage kind of fine-tuned that pre-trained network using self-play. The new version of AlphaGo 0 uses no dataset whatsoever. It does not use any professional gameplay from humans. It learns entirely by self-play. And for people who have a little bit of a background in reinforcement learning, this might sound very surprising. Because many of you will know that if you train a network using only self-play, your network becomes very, very unstable. This was actually the top question on the Reddit Q&A. And the answer that the AlphaGo DeepMind team gave is that it is actually the Monte Carlo tree search that stabilizes the self-play training process so well. So the training stage goes as follows. You get a board representation, you run it through your network, which will initially contain random weights, and you get this output. Let's look at the policy vector. In the beginning, this policy vector will be random. So what you do is you select a bunch of these possible moves, and you select the ones that have the highest probability. So you're going to assume that the ones that have high probabilities are also potentially the strongest moves. You select those moves, and then based on those moves, you get a bunch of different game states, because you're going to play each and every single one of those moves from your top policy vector results, and you're going to actually simulate playing those moves. You end up with a bunch of new board states, and then for every single one of those board states, you're going to repeat the process. And so in the end, what ends up happening is that your current board position that you're evaluating is actually going to explode into this gigantic tree of possible board states that's going to expand and expand as you run through more and more simulations. And the idea is that if you explode this search tree, you can go onto a certain depth, because obviously the explosion is going to be exponential and you are limited by the computational power of your infrastructure. So the AlphaGo team, they decided to play about 1,600 simulations for every single board evaluation. So that means that for every single board state, you're going to run the Monte Carlo tree search until you have exactly 1,600 simulations. And at that point, you're going to use your value network. So the value network is going to decide, okay, which of these board positions are actually good ones? Which ones am I potentially going to win? And then you can back up all those values all the way up to the top of your network. And then you have this very solid estimate of which moves are strong and which moves are not so strong. To give you an example of this, they included a very interesting graph in the paper, which shows you the performance of the AlphaGo network in different versions. So you can see the light blue color is the AlphaGo version that won against Lee Sedol. But then the interesting thing is the lower bar on the left side, the gray bar, because that one actually represents the ELO strength of the network without using Monte Carlo tree search. So if you were to take the network as it is trained, fully trained, but you're only using it once, so you took a board position, you run it through the network, and then you select the single best move from that policy vector without doing any Monte Carlo tree search, you end up with the strength that you see there in the graph. So even though we deep learning enthusiasts might think that this is a great victory for deep learning, I think we should keep in the back of our minds that raw computational force by actually using a lot of those simulated board states is still a very big part of the solution. An additional note to that is that this procedure is very specific to a game like Go, where you have perfect information games and you also have a perfect simulator. Because in this case, in the game of Go, you can select a potential move and then you can simulate everything that would happen down that path in the search tree. But in the real world, that is usually not possible. So having a perfect simulator in this case is a very, very big advantage that you normally wouldn't have in the real world. Let's take a look at some graphs in the paper. Here you can see the training procedure of the AlphaGo 0 network when compared to a purely supervised learning approach. And what is very interesting to me is, for example, the middle one, it shows you the prediction accuracy that the network has on a data set of professional moves. So it turns out that you can actually see in this graph that AlphaGo plays the game of Go differently than a human professional would. But also notingly, if you look at the right graph, you can definitely see that the AlphaGo Zero network is much better at predicting the outcome of the game, you know, whose side is going to win, white or black, based on the current board position. And this graph is also very interesting because it shows you what the effects are of transitioning from a normal convolutional architecture to a residual network. So if you look at the left graph, the blue bottom bar on the right side is the original network that was used in the previous version. And then the red one is actually where they combine both the policy vector and the value representation in a single network using only the same convolutional stack. So you can see a major improvement in ELO rating there. The same improvement, or almost the same improvement, is made when you go from the original paper to a residual architecture. So by just switching out the normal convolutions with residual connections, you actually get a very strong improvement as well. And then if you combine the two in a single network, both using residual connections and using the combination of value representation and policy vector, then you get the purple bar, which is the final system. And then to finalize here, this is a very interesting graph as well. It shows you a couple of the very known moves in the game of Go. So the game of Go has been, it's been around for thousands of years, and there are some very strong potential moves that are known. And things like, the knight's move, or a one-space jump, or a 3-3 invasion, these things, they have gotten names because they are very known and strong tactics. And you can see for some of them that AlphaGo actually discovers them using only self-play, but then after a while it figures out stronger tactics and it doesn't use these as much anymore. So kind of interesting to see that. Right, so that was my take on the AlphaGo Zero paper. Amazing results from the Google DeepMind team. I hope you all learned something. If there are questions that I didn't address, please post them in the comments down below. And I hope to see you next time in the next episode of Archive Insights.